Right now, as you're watching this, there are about 60 volcanoes erupting somewhere on Earth. That's 60 mountains literally breathing fire and reshaping our planet while you sit here. But what if I told you that without these fire-breathing giants, you wouldn't even exist? That the very ground you're standing on, the air you're breathing, even the water you drink, all of it exists because of volcanic fury that's been raging for over 4 billion years. I'm about to take you on a journey deep into the heart of our planet where temperatures reach over 2,000 degrees and molten rock flows like rivers of liquid fire. We're going to discover how these incredible forces don't just destroy, they create. They build continents, make atmospheres, and turn barren rock into the living world we know today. But here's the thing that's going to blow your mind. Volcanoes aren't just random explosions of fire and rock. They're part of an incredibly complex system that's been running like clockwork for billions of years. And understanding how they work will completely change how you see our planet. Most people think volcanoes are just dangerous mountains that explode sometimes. When we see news about volcanic eruptions, we hear about destruction, evacuations, and ash clouds disrupting flights. But this view misses something huge. It's like looking at a forest fire and only seeing the flames, without understanding that fire is actually essential for forest health and new growth. The real challenge isn't understanding what volcanoes do. It's understanding why they do it and how their seemingly destructive power is actually the most creative force on our planet. How can something so violent and dangerous also be the reason life exists on Earth? How can mountains that spew deadly gases and molten rock also be responsible for creating the breathable atmosphere that keeps us alive? This contradiction has puzzled humans for thousands of years. Ancient civilizations created gods to explain volcanic activity, from Vulcan in Roman mythology to Pele in Hawaiian culture. They sensed that these mountains held incredible power, but they couldn't understand the deeper mechanisms at work. Even today, with all our scientific knowledge, most people still don't grasp the full picture of how volcanoes actually shape our world. Let me paint you a picture of what's happening beneath your feet right now. Imagine you could slice the earth like an apple and look inside. What you'd see would be absolutely mind-blowing. About 4,000 miles down, at the very center of our planet, there's a solid iron ball that's roughly the size of the moon. This inner core is surrounded by a liquid outer core made of molten iron and nickel, spinning and churning at temperatures over 5,000 degrees Celsius. That's hotter than the surface of the sun. This liquid metal ocean creates Earth's magnetic field, the invisible shield that protects us from deadly solar radiation. But we're not going that deep today. We're interested in what's happening much closer to the surface, in a layer called the mantle. The mantle is a 1,800-mile thick shell of hot rock that surrounds the core. Now, when I say hot rock, I don't mean like rocks sitting in a campfire. I'm talking about rocks so hot it behaves like thick honey, flowing and churning in massive currents that take millions of years to complete one cycle. Think of it like a giant lava lamp, but instead of colored wax, it's rock that's been heated to incredible temperatures. These rock currents, called convection currents, are constantly moving. Hot rock rises toward the surface, cools down, then sinks back toward the core to be heated up again. It's like a massive underground circulatory system that's been running for billions of years. Now, here's where it gets interesting. The Earth's outer layer, the part we live on, isn't one solid piece. It's broken up into massive chunks called tectonic plates, like a cracked eggshell. These plates are floating on top of the flowing mantle rock, and they're constantly moving, just very, very slowly, about as fast as your fingernails grow. But slow doesn't mean weak. These plates are incredibly powerful. When they push against each other, they create mountain ranges like the Himalayas. When they pull apart, they create valleys and ocean basins. And when the hot mantle rock finds a weak spot or a crack between these plates, something magical happens. it rises toward the surface. As this hot rock, which we call magma when it's underground, rises up through the Earth's crust, it starts to change. The pressure decreases as it gets closer to the surface, and gases that were dissolved in the rock start to bubble out, like opening a shaken soda bottle. The magma becomes less dense and rises faster, sometimes shooting up through cracks and weak spots in the crust. When this magma finally reaches the surface and erupts, we call it lava. But the journey from deep mantle rock to surface lava is incredibly complex, and it's this complexity that makes each volcano unique. If you look at a map of the world's volcanoes, you'll notice something strange. They're not scattered randomly across the planet. Instead, they form clear patterns, like dots connected by invisible lines. The most famous of these patterns is called the Ring of Fire, a horseshoe-shaped belt of volcanic activity that surrounds the Pacific Ocean. This ring includes some of the most famous and dangerous volcanoes on Earth: Mount Fuji in Japan, Mount St. Helens in Washington, the volcanoes of Indonesia, the Andes Mountains in South America. They're all part of this fiery necklace that encircles the Pacific. But why do volcanoes cluster in certain areas? The answer lies in those tectonic plates I mentioned earlier. The Ring of Fire marks the edges of the Pacific Plate, where it meets and interacts with other massive pieces of Earth's crust. Imagine two enormous puzzle pieces trying to fit together, but they're both moving in different directions. Sometimes one piece slides under another in a process called subduction. When this happens, the bottom plate gets pushed down into the hot mantle, where it starts to melt. This melted rock has to go somewhere, so it rises back up through the upper plate, creating chains of volcanoes. This is exactly what's happening along the west coast of South America. The oceanic Nazca Plate is sliding under the continental South American plate, creating the incredible volcanic chain of the Andes Mountains. Some of these volcanoes are over 0 feet tall, and contain enough lava to bury entire countries. But subduction isn't the only way volcanoes form. Sometimes plates pull apart from each other, creating rift zones where magma can rise up to fill the gap. The most spectacular example of this is happening right in the middle of the Atlantic Ocean, along something called the Mid-Atlantic Ridge. Picture this. There's a massive underwater mountain range that runs down the center of the Atlantic Ocean, from the Arctic to Antarctica. This ridge is essentially a giant crack in the Earth's crust where new ocean floor is being born. Hot magma constantly rises up through this crack, cools when it hits the cold ocean water, and forms new rock. This process has been going on for millions of years, and it's literally pushing Europe and North America farther apart at the rate of about an inch per year. Most of this volcanic activity happens thousands of feet underwater, where we can't see it. But occasionally, the ridge pokes above the ocean surface, creating volcanic islands. Iceland sits right on top of the Mid-Atlantic Ridge, which is why it has so many active volcanoes and geothermal features like hot springs and geysers. Then there are hotspot volcanoes, which are probably the most mysterious type of all. These volcanoes seem to appear in the middle of tectonic plates, far from any plate boundaries. Scientists think they're caused by columns of extra hot rock called mantle plumes that rise up from very deep in the earth, maybe even from the boundary between the mantle and the core. The Hawaiian Islands are the perfect example of hotspot volcanism. As the Pacific Plate moves over a stationary hotspot, it creates a chain of volcanic islands. The youngest and most active island, the Big Island, sits directly over the hotspot and has some of the most active volcanoes on Earth. As you move northwest along the chain, the islands get older and more eroded because they've moved away from the hotspot. What's really cool is that this hotspot has been active for millions of years, creating not just the Hawaiian Islands we see today, but also a much longer chain of underwater mountains and atolls that stretches all the way to Alaska. It's like a conveyor belt of volcanic island creation that's been running for over 70 million years. Now let's talk about what happens when a volcano actually erupts. The word eruption makes it sound like there's just one type of volcanic explosion, but that's like saying there's only one type of storm. Volcanic eruptions come in many different flavors, each with its own characteristics and dangers. Some eruptions are relatively gentle, like the ones you see in Hawaii. These effusive eruptions pour out streams of lava that flow downhill like red-hot rivers. The lava moves slowly enough that people can usually get out of the way, and while it destroys everything in its path, it rarely kills people directly. These eruptions can go on for months or even years, slowly building up the landscape layer by layer. But other eruptions are absolutely explosive, shooting columns of ash and gas tens of thousands of feet into the air. These explosive eruptions happen when the magma is very viscous, thick and sticky, and contains a lot of dissolved gases. As the magma rises toward the surface, the decreasing pressure causes these gases to expand rapidly, like uncorking a champagne bottle that's been shaken violently. The most dangerous type of explosive eruption creates something called a pyroclastic flow, a fast-moving current of hot gas and volcanic debris that can reach temperatures of over 1,000 degrees Celsius and speeds of 100 miles per hour. These flows are basically avalanches of superheated death that destroy everything in their path. They're so hot they can kill people instantly just from the heat, and they move too fast for anyone to outrun. The eruption of Mount Vesuvius in 79 AD that destroyed Pompeii and Herculaneum was this type of explosive eruption. The pyroclastic flows moved so fast that they buried the cities before most people could escape, preserving them like a snapshot of Roman life frozen in time. But here's what's truly amazing about volcanic eruptions. Even the most destructive ones are acts of creation in disguise. Every time a volcano erupts, it's not just destroying the existing landscape, it's building something new. Let's start with the most obvious way volcanoes create land, by piling up lava and ash to build mountains. The Hawaiian Islands didn't exist 5 million years ago. They were built entirely by volcanic eruptions, layer by layer, from the bottom of the ocean floor. Mauna Loa, the largest volcano on Earth, rises over 30 feet from the ocean floor. That's taller than Mount Everest. And it's still growing. But volcanoes don't just create mountains. They create soil. And not just any soil. Some of the richest, most fertile soil on Earth. When volcanic ash and lava break down over time, they release minerals and nutrients that plants absolutely love. This is why some of the world's most productive agricultural regions are in volcanic areas. Take the island of Java in Indonesia. It has over 140 volcanoes, including some of the most dangerous in the world. You'd think this would make it a terrible place to live, but it's actually one of the most densely populated places on Earth. Why? Because the volcanic soil is so incredibly fertile that it can support intensive agriculture and feed enormous numbers of people. The same thing is true in many other volcanic regions. The slopes of Mount Vesuvius are covered with vineyards and farms because the volcanic soil produces incredible crops. The Pacific Northwest of the United States, with its chain of volcanic mountains, has some of the richest farmland in North America. Even Iceland, with its harsh climate and active volcanoes, can grow crops in volcanic soil heated by geothermal energy. Volcanoes also create entirely new ecosystems. When lava cools and hardens, it forms bare rock that seems lifeless. But life is incredibly persistent and creative. Pioneer species, tough plants and bacteria that can survive in harsh conditions, are usually the first to colonize new volcanic rock. They break down the rock chemically and physically, creating tiny pockets of soil where other plants can take root. Over time, these pioneer communities develop into complex ecosystems. The Hawaiian Islands, which started as completely barren volcanic rock, now host thousands of unique species that evolved specifically to live in volcanic environments. Many of these species exist nowhere else on Earth. Here's where the story gets really mind-blowing. Without volcanoes, Earth would be a dead, airless rock floating in space. Volcanoes didn't just shape the land, they literally created the atmosphere that makes life possible. When Earth first formed about 4.5 billion years ago, it was a hellish place. The surface was covered with oceans of molten rock, and any atmosphere that existed was probably blown away by intense solar winds and asteroid impacts. But as the planet cooled and solidified, volcanoes began pumping gases from the interior out into space. These early volcanic emissions were nothing like the air we breathe today. They were mostly water vapor, carbon dioxide, sulfur compounds, and other gases that would be deadly to us. But these gases were exactly what the early Earth needed to develop a stable atmosphere. The water vapor from volcanoes eventually condensed and fell as rain, creating the first oceans. The carbon dioxide created a greenhouse effect that kept the planet warm enough for liquid water to exist. Other volcanic gases provided the raw materials that early life forms used to evolve and thrive. But volcanoes didn't just create the early atmosphere. They've been regulating it ever since. Earth's atmosphere is like a giant bathtub, with gases constantly being added and removed by various processes. Volcanoes are one of the main faucets filling the tub. Every time a volcano erupts, it releases carbon dioxide that's been stored deep in the earth back into the atmosphere. This carbon dioxide originally came from the atmosphere millions of years ago, got buried in rocks and sediments, and is now being recycled back to the surface. It's like a massive planetary breathing system that operates on geological timescales. This volcanic breathing has helped keep Earth's climate relatively stable over billions of years. When the planet gets too cold, volcanic activity tends to increase, pumping more greenhouse gases into the atmosphere and warming things up. When it gets too hot, chemical processes that remove carbon dioxide from the atmosphere speed up, cooling things down. Of course, this system isn't perfect, and it operates very slowly compared to human timescales. But over the long term, volcanic activity has been crucial for maintaining the conditions that allow life to flourish on Earth. Volcanoes also create local weather patterns and microclimates. The heat from volcanic activity can create updrafts that generate clouds and precipitation. Volcanic mountains can block or redirect wind patterns, creating rain shadows on one side and wet zones on the other. Hot springs and geothermal features create warm pockets that support unique plant and animal communities, even in otherwise harsh climates. In some places, like Iceland and Yellowstone, volcanic heat is so close to the surface that it creates entire landscapes of hot springs, geysers, and steaming vents. These geothermal features aren't just tourist attractions, they're windows into the incredible power that lies just beneath our feet. To really understand how volcanoes have shaped our planet, we need to think in deep time, the vast stretches of millions and billions of years that make up Earth's history. From our human perspective, volcanoes seem like dramatic, short-term events. But from the planet's perspective, they're part of slow, steady processes that have been reshaping the surface for eons. Let's go back to the very beginning. About 4.5 billion years ago, Earth was a very different place. The surface was covered with molten rock, and massive volcanic eruptions were constantly reshaping the landscape. This period, called the Hadean Eon, was like a preview of hell, hence the name. But even during this violent time, volcanoes were doing the essential work of building the first solid crust and beginning to create an atmosphere. As Earth cooled down and entered the Archean Eon about 4 billion years ago, volcanic activity continued to dominate the planet. But now something new was happening. The first primitive life forms were appearing, and they were intimately connected to volcanic activity. These early life forms, mostly bacteria and archaea, often lived in extreme environments around volcanic vents and hot springs. They used chemical energy from volcanic gases instead of sunlight for photosynthesis. In a very real sense, life on Earth was born from fire. Some of the oldest evidence of life on Earth comes from volcanic regions. In Western Australia, there are volcanic rocks over 3.5 billion years old that contain what appear to be fossilized bacteria. In Greenland, scientists have found chemical signatures in volcanic rocks that suggest life existed there 3.8 billion years ago. But these early volcanoes were very different from modern ones. The Earth was much hotter then, so magma was more fluid and eruptions were more frequent and intense. There were also different types of volcanic activity that don't happen anymore, like the massive flood basalt eruptions that could cover entire continents with lava. One of the most important volcanic events in Earth's history happened about 2.5 billion years ago, during something called the Great Oxidation Event. This wasn't a single volcanic eruption, but a series of massive volcanic episodes that fundamentally changed the planet's atmosphere and oceans. Before this time, Earth's atmosphere contained almost no oxygen. But certain types of volcanic activity began releasing gases that reacted with sunlight to produce oxygen. At the same time, early photosynthetic bacteria were also starting to produce oxygen as a waste product. This influx of oxygen was actually toxic to most life forms that existed at the time, causing a mass extinction event. But it also set the stage for more complex life forms that could use oxygen for energy. Without this volcanic contribution to Earth's oxygen supply, complex life as we know it could never have evolved. Throughout Earth's history, major volcanic events have coincided with important biological changes. The Permian-Triassic extinction event 252 million years ago, which killed over 90% of all species on Earth, was triggered by massive volcanic eruptions in what is now Siberia. These eruptions, called the Siberian Traps, released enormous amounts of lava, ash, and toxic gases that poisoned the atmosphere and oceans. But even this devastating event ultimately led to new opportunities for life. The extinction of so many species opened up ecological niches that were filled by new types of organisms, including the early ancestors of dinosaurs. Similar patterns have repeated throughout Earth's history. Major volcanic events cause mass extinctions, but they also create new environments and opportunities that drive evolution in new directions. The volcanic activity that helped kill the dinosaurs 66 million years ago also created conditions that allowed mammals to diversify and eventually dominate terrestrial ecosystems. One of the most amazing things about volcanoes is how they've literally built the continents we live on. When you walk on solid ground, you're walking on rock that was mostly created by volcanic processes over billions of years. The story starts with the earliest crust formation. When Earth first cooled from its molten state, the first solid rocks were formed by volcanic activity. These rocks were different from most modern volcanic rocks. They were richer in magnesium and iron, and they formed the foundations of what would eventually become our continents. But building a continent takes more than just piling up volcanic rock. It requires a complex interplay between volcanic activity, plate tectonics, erosion, and sedimentation that operates over hundreds of millions of years. The process typically starts at the edges of tectonic plates, where volcanic island arcs form. These are chains of volcanoes that develop when one plate subducts beneath another. Over time, these volcanic islands grow larger and eventually collide with continental margins, adding new land to the existing continents. The western coast of North America is a perfect example of this process in action. Over the past 200 million years, numerous volcanic island arcs and oceanic plateaus have crashed into and stuck to the North American continent. Each collision added a new piece of land, gradually building the continent westward. You can actually see evidence of this process if you know what to look for. The rocks in the Sierra Nevada mountains of California are mostly granitic rocks that formed in the roots of ancient volcanoes. The Coast Ranges contain rocks that were originally formed as oceanic volcanic islands thousands of miles out in the Pacific, then scraped off and plastered onto the continent as the Pacific plate moved eastward. This process, called accretion, has added millions of square miles of new land to the continents over Earth's history. It's estimated that about 60% of North America consists of accreted volcanic terranes, pieces of volcanic rock that formed elsewhere and were later added to the continent. But volcanoes don't just add land directly through eruptions. They also contribute to continent building through more subtle processes. Volcanic activity provides the heat that drives mountain building processes. When large bodies of magma intrude into the crust but don't erupt at the surface, they create huge underground chambers called plutons. These plutons push up the overlying rocks, creating mountain ranges. The granite peaks of Yosemite National Park are actually the eroded remains of ancient magma chambers that never erupted. The original volcanic mountains that sat on top of these chambers have been completely worn away by millions of years of erosion, exposing the beautiful granite formations we see today. Volcanic activity also plays a crucial role in the rock cycle, the process by which rocks are continuously transformed from one type to another. Volcanic eruptions create igneous rocks directly, but they also contribute to the formation of sedimentary rocks by providing the weathered material that gets deposited in layers. And the heat from volcanic activity can transform existing rocks into metamorphic rocks. This rock cycle is essential for continental stability. Without the constant recycling of rock material driven by volcanic processes, the continents would eventually be worn down to sea level by erosion. Volcanic activity provides the vertical motion needed to keep building the land upward, balancing the destructive effects of weathering and erosion. Some of the most dramatic examples of volcanic land creation are oceanic islands. These islands literally rise from the ocean floor through pure volcanic power, creating new land where none existed before. The process usually starts thousands of feet below the ocean surface, where hot magma erupts onto the seafloor. At these depths, the enormous water pressure prevents explosive eruptions, so the lava forms rounded, pillow-like shapes as it cools rapidly in the cold seawater. As eruptions continue, the underwater volcano grows taller and wider. Eventually, it reaches shallow water where the decreased pressure allows for more explosive eruptions. Steam explosions occur as hot lava meets seawater, creating dramatic plumes of ash and steam that can be seen from miles away. Finally, the volcanic pile breaks the ocean surface, and a new island is born. But the story doesn't end there. It's really just the beginning. The young island is usually small and unstable, constantly battered by waves and storms. Many newly formed volcanic islands are washed away before they can establish themselves. But if the volcanic activity continues, the island grows larger and more stable. As lava flows reach the sea, they cool and solidify, extending the coastline outward. Over time, the island develops a mature volcanic landscape with multiple cones, craters, and lava flows. The Hawaiian Islands provide the best example of this process. The Big Island is currently in its youth, with active volcanoes constantly adding new land. Kilauea volcano has been erupting almost continuously for over 35 years, adding hundreds of acres of new land to the island. As you move northwest along the Hawaiian chain, you can see how volcanic islands age and evolve. The older islands have been eroded by millions of years of wind and rain, creating dramatic valleys and cliffs. Some, like Kauai, have been so heavily eroded that they barely resemble their original volcanic forms. Eventually, volcanic islands may sink back below sea level as the oceanic crust they sit on cools and contracts. But even then, they leave behind evidence of their existence in the form of seamounts, underwater mountains that mark the locations of ancient islands. This process of volcanic island creation has been going on for hundreds of millions of years. The Pacific Ocean is dotted with thousands of volcanic islands and seamounts, each representing a story of fire rising from the depths to create new land. But oceanic volcanoes don't just create islands, they create entire ecosystems from scratch. When a new volcanic island first emerges from the sea, it's completely sterile, just bare rock with no life whatsoever. But life is incredibly good at finding and colonizing new habitats. The first organisms to arrive are usually carried by wind or ocean currents, bacteria, fungal spores, and seeds that can survive long journeys across open ocean. These pioneer species begin the slow process of breaking down volcanic rock and creating soil. Over thousands of years, more complex ecosystems develop as new species arrive and evolve. Many volcanic islands become biodiversity hotspots, home to unique species that exist nowhere else on Earth. The Galapagos Islands, which inspired Darwin's theory of evolution, are a perfect example of how volcanic islands can become laboratories of speciation and adaptation. While we often think of volcanoes as local phenomena, they actually have the power to influence climate and weather patterns on a global scale. Large volcanic eruptions can affect global temperatures, precipitation patterns, and atmospheric chemistry for years or even decades after the eruption. This happens because explosive volcanic eruptions inject enormous quantities of ash and gases high into the atmosphere, sometimes reaching the stratosphere 30 miles above Earth's surface. At these altitudes, volcanic material can spread around the entire planet, carried by high-altitude winds. The most significant climate effect comes from sulfur dioxide gas released by volcanoes. In the upper atmosphere, sulfur dioxide reacts with water vapor to form tiny sulfuric acid droplets that reflect sunlight back to space. These droplets act like a giant mirror in the sky, reducing the amount of solar radiation that reaches Earth's surface. The result is global cooling that can last for several years. The 1,991 eruption of Mount Pinatubo in the Philippines, for example, reduced global average temperatures by about 1 degree Fahrenheit for nearly 3 years. That might not sound like much, but it's huge in terms of global climate. Some volcanic eruptions have caused even more dramatic climate effects. The 1,815 eruption of Mount Tambora in Indonesia ejected so much material into the atmosphere that it caused the year without a summer in 1,816. Temperatures dropped so much that crops failed across Europe and North America, leading to famine and social unrest. But volcanoes don't just cool the climate, they can also warm it through their emissions of carbon dioxide and other greenhouse gases. Most individual eruptions release relatively small amounts of CO2 compared to human activities, but sustained volcanic activity over long periods can contribute significantly to atmospheric greenhouse gas concentrations. During periods of intense volcanic activity, like the formation of large igneous provinces, the climate warming from volcanic CO2 emissions can be enormous. The Permian-Triassic extinction event 252 million years ago was likely caused partly by massive volcanic CO2 emissions that created extreme global warming. Volcanoes also influence regional climate patterns through their effects on atmospheric circulation. Large volcanic mountains can block or redirect air currents, creating rain shadows on their leeward sides and enhanced precipitation on their windward sides. The volcanic peaks of the Cascade Range in the Pacific Northwest create a dramatic rain shadow effect. The western slopes of these mountains receive enormous amounts of rainfall, creating lush, temperate rainforests. But just a few dozen miles east, the landscape is much drier because the mountains have wrung most of the moisture out of the air. Volcanic activity also creates unique microclimates through geothermal heating. Areas around active volcanoes often have warmer temperatures than surrounding regions, allowing different plant and animal communities to survive in otherwise inhospitable climates. In Iceland, geothermal heat from volcanic activity allows tropical plants to grow in greenhouses, even though the country is just below the Arctic Circle. Some communities in volcanic regions have used geothermal energy for heating and agriculture for thousands of years. One of the most amazing aspects of volcanic environments is how life manages to not just survive, but thrive in conditions that would be instantly lethal to most organisms. Volcanic regions host some of the most extreme and unique ecosystems on Earth, home to creatures that have evolved incredible adaptations to deal with heat, toxic gases, and unstable terrain. The most extreme volcanic environments are the deep sea hydrothermal vents, where seawater meets hot volcanic rock on the ocean floor. These vents spew superheated water rich in toxic chemicals like hydrogen sulfide, creating conditions that seem completely hostile to life. Temperatures can reach over 400 degrees Celsius, and the water is highly acidic. Yet, these vents support thriving ecosystems unlike anything else on Earth. Giant tube worms up to 8 feet long live right next to the vents, their bodies housing bacteria that convert toxic chemicals into food. Ghostly white crabs scuttle across the scalding rocks, and strange fish with antifreeze proteins in their blood swim through the superheated water. These vent ecosystems are completely independent of sunlight. Instead of photosynthesis, they're based on chemosynthesis, the process of using chemical energy to create food. This discovery revolutionized our understanding of life on Earth and suggested that life might exist in similar extreme environments on other planets. On land, volcanic environments also host remarkable life forms. Some bacteria can survive in hot springs with temperatures over 80 degrees Celsius, thriving in water that would instantly kill most organisms. These thermophilic bacteria have evolved special proteins and enzymes that remain stable at high temperatures. Plants have also evolved fascinating adaptations to volcanic environments. Some species can grow directly on fresh lava flows, their roots finding tiny cracks in the rock where they can establish themselves. Others have developed the ability to tolerate high levels of sulfur and other toxic volcanic gases. The silversword plants of Hawaii are a perfect example of volcanic adaptation. These striking plants, which look like giant silver pine cones, grow only on the volcanic slopes of Maui's Haleakala crater. They've evolved to handle the extreme temperature fluctuations, intense UV radiation, and nutrient-poor volcanic soil of their high-altitude volcanic habitat. Animals have also found ways to exploit volcanic environments. Some birds nest in warm volcanic sand, using geothermal heat to incubate their eggs. Certain reptiles bask on sun-warmed volcanic rocks, taking advantage of the heat-absorbing properties of dark volcanic stone. In Yellowstone National Park, bison and elk often gather around hot springs during winter, using the geothermal heat to stay warm in the harsh mountain climate. Some insects have evolved to live exclusively in the warm zones around volcanic features. But perhaps the most remarkable thing about life in volcanic environments is how quickly it can recover after eruptions. Areas that have been completely sterilized by volcanic activity can be recolonized by life within just a few years. After Mount St. Helens erupted in 1980, scientists expected the devastated landscape to remain lifeless for decades. But they were amazed to find that plants and animals began returning much more quickly than anticipated. Seeds survived in protected pockets, roots remained alive underground, and animals recolonized the area from surrounding regions. Within just a few years, the blast zone was showing signs of ecological recovery. Today, over 40 years later, much of the area has been recolonized by diverse plant and animal communities, though the ecosystem is still different from what existed before the eruption. This rapid recovery shows how resilient life can be, and how volcanic disturbances, while destructive in the short term, can actually increase biodiversity over longer time periods by creating new habitats and ecological opportunities. Hidden beneath many volcanic landscapes are vast networks of caves and tunnels created by flowing lava. These underground worlds, called lava tubes, are some of the most fascinating and little-known features of volcanic terrain. Lava tubes form when the surface of a lava flow cools and hardens while molten lava continues to flow underneath. As the eruption ends and the lava drains away, it leaves behind hollow tunnels that can extend for miles underground. These tubes come in all sizes, from narrow passages you can barely crawl through to massive caverns big enough to hold a cathedral. The Kazumura cave system on Hawaii's Big Island is the longest lava tube in the world, stretching for over 40 miles underground and descending more than 600 feet below the surface. Inside lava tubes, you enter an alien world shaped entirely by fire. The walls show the frozen patterns of flowing lava, ropey textures, drip formations, and smooth surfaces polished by the passage of molten rock. The floors may be covered with breakdown material from collapsed ceilings, or they may preserve the original lava flow surface with its characteristic textures. Some lava tubes contain unique formations found nowhere else on Earth. Lava stalactites, called lavasicles, hang from the ceiling where dripping lava cooled and solidified. Mineral deposits left by groundwater can create colorful formations on the cave walls. The temperature inside lava tubes is usually constant year-round, typically matching the average annual temperature of the surface above. This stable environment makes them ideal habitats for specialized cave life. Many lava tubes host unique ecosystems adapted to the dark, humid environment underground. Blind cave spiders, pale crickets, and other creatures that have lost their pigmentation and eyesight over generations live their entire lives in these volcanic caves. Some lava tubes contain pools of water fed by underground streams or seepage from above. These underground lakes can be crystal clear and incredibly pure, filtered through layers of porous volcanic rock. Humans have been using lava tubes for thousands of years. In Hawaii, ancient Polynesians used them as shelters, burial sites, and storage areas. During World War II, people in volcanic regions used lava tubes as bomb shelters. Today, lava tubes are important for scientific research. They provide insights into volcanic processes and help scientists understand how lava behaves during eruptions. They're also being studied as analogs for caves that might exist on Mars and the Moon, helping scientists prepare for future space exploration. Some of the most spectacular lava tubes are those that extend underwater. When lava flows reach the ocean, they can continue flowing underwater, creating submarine lava tubes. These underwater tunnels provide unique habitats for marine life and can extend for miles beneath the seafloor. The formation of underwater lava tubes is a dramatic process. When 2,000-degree lava meets cold seawater, it creates massive steam explosions and forms a protective crust almost instantly. But underneath this crust, the lava keeps flowing, carving out tunnels in the sea floor. These submarine tubes often connect to land-based cave systems, creating vast underground networks that span from mountain slopes all the way to the ocean depths. Some of these systems are so extensive that they form underground rivers of lava that can transport molten rock for dozens of miles from the original eruption site. Exploring lava tubes is like traveling through the circulatory system of a sleeping giant. Each tunnel tells a story about the eruption that created it, the speed of the lava flow, the temperature of the molten rock, and the conditions that existed during the eruption. Scientists study lava tubes to understand volcanic processes better, but they also use them to prepare for space exploration. The lava tubes on Earth are very similar to those that likely exist on Mars and the Moon, making them perfect training grounds for future cave exploration on other worlds. Every volcanic rock is like a page in Earth's history book, containing information about the conditions that existed when it formed. By studying volcanic rocks and deposits, scientists can reconstruct the story of our planet's past with incredible detail. Volcanic ash layers, called tephras, are particularly valuable for understanding Earth's history. When a volcano erupts explosively, it can scatter ash over enormous areas, sometimes covering entire continents with a distinctive layer of volcanic debris. These ash layers act like timestamps in the geological record, marking specific moments in Earth's past. Scientists can date these ash layers using various techniques, creating a chronological framework for understanding when different events occurred. They can also analyze the chemical composition of the ash to identify which volcano it came from, even if the eruption happened millions of years ago. One of the most famous volcanic ash layers is the one created by the Yellowstone supervolcano about 630 years ago. This ash layer, called the Lava Creek Tuff, can be found in rocks across much of the western United States, providing evidence of one of the largest volcanic eruptions in Earth's recent history. But volcanic rocks contain much more information than just their age. The minerals in volcanic rocks can tell us about the temperature and pressure conditions deep in the earth when the magma formed. The presence of certain elements can reveal information about the composition of the mantle and how it has changed over time. Gas bubbles trapped in volcanic glass, called melt inclusions, preserve samples of the original magma composition before it was modified by eruption processes. These tiny time capsules allow scientists to study the chemistry of ancient volcanic systems in incredible detail. The magnetic properties of volcanic rocks are particularly interesting because they record the direction and intensity of Earth's magnetic field when the rock cooled. Since Earth's magnetic field has reversed many times throughout history, volcanic rocks provide a record of these magnetic reversals that helps scientists understand how the planet's magnetic field works. By studying volcanic rocks from different time periods, scientists have discovered that Earth's volcanic activity has varied dramatically throughout history. There have been periods of intense volcanic activity called large igneous province events, when massive amounts of lava cover huge areas of the planet's surface. These events often coincide with major changes in Earth's climate and biosphere. The Deccan Traps in India, formed by one such event around 66 million years ago, may have contributed to the extinction of the dinosaurs. The Siberian Traps, formed 252 million years ago, are linked to the greatest mass extinction in Earth's history. Understanding these past volcanic events helps scientists assess the potential impacts of future large-scale volcanic activity. While such massive eruptions are extremely rare, they represent one of the few natural phenomena that could significantly impact global civilization. Volcanic rocks also preserve evidence of ancient life forms. In some cases, volcanic ash has buried and preserved organisms so perfectly that scientists can study details of their anatomy and behavior. The famous fossil site at Asheville Fossil Beds in Nebraska preserves animals that were buried by volcanic ash from eruptions in Yellowstone about 12 million years ago. Even more remarkably, some volcanic rocks preserve actual samples of ancient atmospheres. When lava erupts underwater or in swampy environments, it can trap bubbles of ancient air or water. By analyzing these trapped gases, scientists can study how Earth's atmosphere has changed over millions of years. Throughout history, certain volcanic landscapes have captured human imagination and become legendary for their beauty, power, or cultural significance. These iconic volcanic regions tell stories not just of geological processes, but of human interaction with the awesome forces of nature. Mount Vesuvius in Italy is probably the most famous volcano in the world, not just because of its devastating eruption in 79 AD, but because of how perfectly it preserved the Roman cities of Pompeii and Herculaneum. The pyroclastic flows that destroyed these cities also created an unparalleled archaeological treasure, preserving details of daily life in the Roman Empire that would otherwise have been lost forever. But Vesuvius is more than just a historical curiosity. It's still an active and dangerous volcano that looms over Naples, one of Europe's largest cities. Over 3 million people live in the shadow of Vesuvius, making it one of the most dangerous volcanoes in the world in terms of potential human impact. The volcano's fertile slopes are covered with vineyards and farms that take advantage of the rich volcanic soil. The wine produced from grapes grown on Vesuvius has a distinctive mineral taste that reflects the volcanic terroir. It's a perfect example of how humans have learned to live with and even benefit from volcanic activity, despite the ever-present danger. Mount Fuji in Japan represents a different aspect of human-volcano relationships. This nearly perfect volcanic cone has been sacred to the Japanese people for over 1,000 years. Climbing Mount Fuji is considered a spiritual journey, and the mountain appears in countless works of art, including the famous woodblock prints by Hokusai. Mount Fuji hasn't erupted since 1707, but it's still considered an active volcano. The Japanese government constantly monitors it for signs of renewed activity, knowing that an eruption could have enormous impacts on the Tokyo metropolitan area, home to over 35 million people. The mountain's perfect shape is the result of multiple eruptions that have built up its cone over thousands of years. But this beauty comes with danger. Mount Fuji's eruptions can be explosive, and the mountain is located at the junction of 3 tectonic plates, making it seismically active. Yellowstone National Park in the United States showcases a completely different type of volcanic landscape. Unlike cone-shaped volcanoes like Vesuvius and Fuji, Yellowstone sits on top of a massive underground magma chamber that occasionally produces supervolcanic eruptions. The last major eruption at Yellowstone occurred 630 years ago and was so large that it ejected over 10 cubic kilometers of material, enough to bury the entire state of Texas under a foot of volcanic debris. This eruption created the Yellowstone caldera, a massive depression about 30 miles wide that forms the heart of the park. Today, Yellowstone's volcanic activity manifests as thousands of hot springs, geysers, and fumaroles that create a surreal landscape of steaming pools and erupting waterspouts. The famous Old Faithful geyser is just one of over 10. 0 geothermal features in the park, all powered by the enormous magma chamber below. The geothermal features of Yellowstone support unique ecosystems of thermophilic bacteria that create brilliant colors in the hot springs. The rainbow-colored terraces and pools look almost alien, like landscapes from another planet. Iceland represents yet another type of volcanic landscape, one shaped by its position on the mid-Atlantic ridge. The island is essentially the above-water portion of a massive underwater volcanic system, and it's one of the most volcanically active places on Earth. Iceland's volcanic landscapes are incredibly diverse, ranging from active lava fields and steaming fumaroles to massive ice-covered volcanoes. The interaction between ice and fire creates some of the most dramatic geological processes on Earth. When volcanoes erupt beneath ice sheets, they create explosive interactions that can cause massive flooding and ash clouds. The 2010 eruption of Eyjafjallajökull, an ice-covered volcano with an unpronounceable name, created an ash cloud that disrupted air travel across Europe for weeks. But Iceland's volcanoes also provide enormous benefits. The country gets most of its electricity and heating from geothermal energy, making it one of the most sustainable energy systems in the world. Geothermal power plants tap into the heat from volcanic activity to generate clean, renewable energy. The volcanic landscapes of Iceland are also incredibly beautiful, featuring black sand beaches created by volcanic eruptions, dramatic waterfalls cascading over volcanic cliffs, and colorful geothermal areas that attract visitors from around the world. The Hawaiian Islands represent perhaps the purest example of volcanic creation on Earth. These islands were built entirely by volcanic eruptions, rising from the deep ocean floor to create some of the most spectacular landscapes in the world. Each Hawaiian island represents a different stage in volcanic evolution. The Big Island, still actively growing from ongoing eruptions, showcases active lava flows, steaming craters, and new land being created before your eyes. You can literally watch the island grow as lava flows into the ocean and creates new coastline. Moving northwest along the island chain, you can see how volcanic islands age and evolve. The older islands have been sculpted by millions of years of erosion into dramatic valleys, towering cliffs, and knife-edge ridges that create some of the most breathtaking scenery on Earth. The volcanic soils of Hawaii support incredible biodiversity, with many species found nowhere else in the world. But the islands also show how human activity can impact volcanic ecosystems, as introduced species and development have threatened many native Hawaiian plants and animals. One of the most important aspects of living with volcanoes is trying to predict when they might erupt. Volcanic eruptions can be incredibly destructive, but unlike earthquakes, they usually give warning signs that scientists can detect and interpret. Modern volcano monitoring uses a combination of seismology, gas analysis, ground deformation measurement, and thermal imaging to track changes in volcanic systems. These techniques have revolutionized our ability to forecast volcanic eruptions and warn people of impending danger. Seismic monitoring is often the first line of defense in volcano watching. As magma moves underground, it creates earthquakes that can be detected by sensitive instruments. The patterns of these earthquakes can tell scientists a lot about what's happening inside the volcano. When magma starts rising toward the surface, it typically creates swarms of small earthquakes as it breaks through rock barriers. These earthquake swarms often start weeks or months before an eruption, giving scientists time to issue warnings and help people prepare. The depth and frequency of earthquakes can also provide clues about how close an eruption might be. Shallow earthquakes directly beneath a volcano's summit often indicate that magma is very close to the surface and an eruption is imminent. Ground deformation monitoring uses GPS and satellite imagery to detect tiny changes in the shape of volcanic mountains. When magma accumulates underground, it can push up the surface, creating bulges that can be measured with incredible precision. Before Mount St. Helens erupted in 1980, the north side of the mountain bulged outward by over 6 feet as magma pushed up from below. This deformation was one of the key warning signs that led scientists to predict the eruption and evacuate the area. Today, scientists use satellite radar to monitor ground deformation at volcanoes around the world. This technology can detect changes as small as a few millimeters from space, allowing researchers to track volcanic unrest even in remote areas. Gas monitoring is another crucial tool for volcano forecasting. Different gases are released at different stages of volcanic activity, and changes in gas composition or emission rates can indicate changes in the volcanic system. Sulfur dioxide is particularly important because it's released when fresh magma rises toward the surface. Increased sulfur dioxide emissions often precede volcanic eruptions by days or weeks. Scientists use special instruments to measure gas emissions from aircraft, satellites, and ground-based stations. Carbon dioxide monitoring is also important because this gas can accumulate in dangerous concentrations in low-lying areas around volcanoes. Several people have died from carbon dioxide poisoning in volcanic areas, making gas monitoring crucial for public safety. Thermal monitoring uses infrared cameras and satellites to detect changes in temperature at volcanic vents and lava domes. Rising magma temperatures can be detected weeks before visible eruptions begin, providing another tool for eruption forecasting. Satellite thermal monitoring has become particularly important for tracking remote volcanoes that would be difficult or dangerous to monitor on the ground. Scientists can now track volcanic activity anywhere in the world using thermal satellites. Despite all these monitoring techniques, predicting exactly when a volcano will erupt remains challenging. Volcanic systems are incredibly complex, and each volcano behaves differently. Some volcanoes give clear warning signs weeks or months in advance, while others can erupt with little warning. The goal of volcano monitoring isn't necessarily to predict eruptions to the exact day and hour, but to provide enough warning to save lives and minimize damage. Even a few days or weeks of warning can allow authorities to evacuate dangerous areas and prepare for the impacts of an eruption. One of the biggest challenges in volcano forecasting is distinguishing between volcanic unrest that will lead to an eruption and unrest that will simply fade away without an eruption. Many volcanoes show signs of unrest, earthquakes, gas emissions, ground deformation that never result in eruptions. This uncertainty creates difficult decisions for scientists and emergency managers. Issue too many false alarms, and people may stop taking warnings seriously. Wait too long to issue warnings, and people may not have enough time to evacuate safely. The 2018 eruption of Kilauea volcano in Hawaii demonstrates both the successes and challenges of volcano monitoring. Scientists detected increased seismic activity weeks before the main eruption began, allowing them to warn residents of the lower Puna district that an eruption was possible. When the eruption did begin, it followed patterns that scientists had predicted based on previous eruptions. Lava flows moved slowly enough that people could evacuate safely, and no lives were lost directly to the eruption. However, the eruption destroyed over 700 homes and completely changed the landscape of the affected area. The Kilauea eruption also showed how volcanic activity can evolve in unexpected ways. While scientists predicted that an eruption would occur, they couldn't predict exactly where lava would flow or how long the eruption would last. The eruption continued for several months, much longer than many people expected. Volcano monitoring has saved countless lives over the past few decades. The 1,991 eruption of Mount Pinatubo in the Philippines could have killed tens of thousands of people, but advanced warning based on seismic and gas monitoring allowed authorities to evacuate over 200 people from the danger zone. Similarly, monitoring of Mount Vesuvius has helped Italian authorities develop detailed evacuation plans for the Naples area. While Vesuvius hasn't erupted since 1944, continuous monitoring ensures that scientists will detect the first signs of renewed activity. But volcano monitoring faces significant challenges, especially in developing countries where many dangerous volcanoes are located. Installing and maintaining monitoring equipment is expensive, and interpreting the data requires trained scientists and sophisticated analysis tools. International organizations and developed countries are working to improve volcano monitoring capabilities in high-risk areas. The Volcano Disaster Assistance Program, run by the United States Geological Survey, provides emergency monitoring equipment and expertise to countries facing volcanic crises. One of the most surprising aspects of volcanic landscapes is how incredibly fertile they become over time. Areas that were completely sterilized by volcanic eruptions can transform into some of the most productive agricultural land on Earth. This transformation happens because volcanic materials are rich in minerals and nutrients that plants need to grow. When volcanic ash and lava break down through weathering processes, they release elements like potassium, phosphorus, calcium, and magnesium that are essential plant nutrients. These minerals are often present in higher concentrations in volcanic soils than in soils derived from other rock types. Volcanic ash is particularly valuable for soil formation because it breaks down relatively quickly and has a very fine texture that retains water well. The porous nature of many volcanic materials also allows for good drainage and aeration, creating ideal conditions for root growth. The island of Java in Indonesia provides a perfect example of volcanic soil fertility. Despite having some of the most active and dangerous volcanoes in the world, Java supports one of the highest population densities on Earth, over 1 0 people per square kilometer. This is possible only because the volcanic soils are so incredibly productive that they can support intensive agriculture. Javanese farmers have learned to work with volcanic activity using the fresh ash from eruptions as natural fertilizer. They've developed agricultural systems that can quickly recover from volcanic disturbances and take advantage of the soil fertility that results from eruptions. The slopes of Mount Vesuvius in Italy tell a similar story. Despite the obvious dangers of living near an active volcano, the area around Vesuvius has been continuously farmed for over 20 years. The volcanic soil produces exceptional wines, and the San Marzano tomatoes grown in volcanic soil near Naples are considered among the best in the world. Volcanic soils often have distinctive characteristics that affect the flavor of crops grown in them. The mineral content of volcanic soil can create unique terroir effects in wine, coffee, and other crops. Many premium agricultural products come from volcanic regions specifically because of these soil characteristics. The coffee-growing regions of Central America, many of which are located on volcanic slopes, produce some of the world's finest coffee beans. The volcanic soils provide excellent drainage and mineral content that contributes to the complex flavors that make these coffees so prized. In Hawaii, the volcanic soils of Kona District produce coffee that commands premium prices on the world market. The unique combination of volcanic soil, tropical climate, and elevation creates ideal conditions for coffee cultivation. But farming in volcanic areas requires special knowledge and techniques. Farmers must understand how to work with soils that may be very young and still developing their structure. They need to know how different types of volcanic materials affect plant growth and how to manage the challenges that come with living in an active volcanic environment. One of the biggest challenges is the unpredictability of volcanic activity. Farmers may invest years in developing productive fields, only to have them buried by lava flows or ash falls. This risk requires resilient farming systems and often government support to help farmers recover from volcanic disasters. The time it takes for volcanic materials to break down into fertile soil varies greatly depending on the type of volcanic material and the climate. In tropical areas with high rainfall, volcanic ash can develop into productive soil within just a few years. In drier climates, the process may take decades or centuries. Some of the youngest productive soils on Earth are found in volcanic regions. In Hawaii, farmers are growing crops on lava flows that are only a few decades old. Pioneer plants help break down the rock and begin soil formation, creating pockets of soil where crops can be established. The relationship between volcanoes and agriculture goes beyond just soil fertility. In some regions, volcanic activity provides other benefits for farming. Geothermal heat from volcanic activity can be used to warm greenhouses, extend growing seasons, and even power agricultural processing facilities. Iceland uses geothermal energy from volcanic activity to heat greenhouses where they grow tropical fruits and vegetables despite the country's cold climate. This allows Iceland to produce fresh produce year-round and reduce their dependence on imported food. Volcanic regions also often have abundant water resources because volcanic rocks are good at storing groundwater. The porous nature of many volcanic rocks creates natural aquifers that can supply water for irrigation even during dry periods. However, farming in volcanic areas also presents unique challenges. Volcanic soils may be deficient in certain nutrients or may have chemical characteristics that require special management. Some volcanic soils are very acidic, requiring lime applications to neutralize the pH for optimal crop growth. Heavy metal contamination can also be a concern in some volcanic soils, particularly those near active vents or fumaroles. Farmers in these areas may need to test their soils regularly and take precautions to prevent contamination of crops. Despite these challenges, many of the world's most productive agricultural regions are located in volcanic areas. The combination of fertile soils, reliable water supplies, and often favorable climates makes volcanic regions ideal for intensive agriculture. Understanding the relationship between volcanoes and soil fertility has important implications for global food security. As the world's population continues to grow, we'll need to maximize agricultural productivity on available land. Volcanic soils represent some of the most fertile land on Earth, and learning how to manage them sustainably will be crucial for feeding the world's growing population. Here's the moment that changes everything about how you see our planet. Earth isn't a stable, finished world with volcanoes as occasional interruptions. Earth is volcanic activity. Everything around you, the ground you walk on, the air you breathe, the water in your body, exists because our planet is essentially a volcanic machine that's been running for over 4 billion years. Think about this for a moment. Right now, as you're listening to this, the continents are slowly drifting across the globe, pulled by currents of molten rock thousands of miles below your feet. The Atlantic Ocean is growing wider by about 2 inches every year, as underwater volcanoes create new seafloor along the mid-Atlantic ridge. The Pacific Plate is sliding under other continents, recycling old ocean floor back into the mantle where it will be melted down and eventually rise again as new volcanic rock. This isn't a slow, dead process happening on geological timescales that don't matter to us. This is a living, breathing planetary system that affects everything about our daily lives. The weather patterns that determine whether it rains on your garden are influenced by volcanic mountains that redirect air currents. The fertility of the soil that grows your food comes from ancient volcanic eruptions that scattered mineral-rich ash across the landscape. Even the magnetic field that protects you from deadly cosmic radiation is generated by the same heat engine that drives volcanic activity. But here's the truly mind-blowing part. This volcanic system isn't random or chaotic. It's been running like a perfectly tuned engine for billions of years, maintaining conditions that allow life to exist. When the climate gets too cold, increased volcanic activity pumps greenhouse gases into the atmosphere and warms things up. When it gets too hot, weathering of volcanic rocks removes carbon dioxide from the atmosphere and cools things down. This system has survived asteroid impacts that vaporized entire seas, ice ages that froze most of the planet, and massive changes in atmospheric chemistry. Through all of these catastrophes, volcanic activity has continued to remake the surface of the Earth, creating new land, new atmospheres, and new opportunities for life to evolve and thrive. And we're not just passive observers of this system, we're products of it. The calcium in your bones came from ancient coral reefs that were built on volcanic islands. The iron in your blood was forged in the cores of dying stars and delivered to Earth by volcanic processes. The oxygen you're breathing right now was first released into the atmosphere by volcanic activity billions of years ago. Every breath you take is part of a cycle that includes the deepest parts of the Earth. The carbon dioxide you exhale may eventually be absorbed by the ocean, incorporated into seafloor sediments, subducted into the mantle, and eventually released again by a volcanic eruption decades or centuries from now. You are part of the Earth's volcanic system, and it is part of you. The boundary between living things and the geological processes that shape our planet is much more fluid than most people realize. Life and volcanoes have been partners for billions of years, each shaping and being shaped by the other in an endless dance of creation and destruction. This realization changes how you see natural disasters. Volcanic eruptions aren't interruptions of the natural order. They are the natural order. They're part of the same system that created the continents, the oceans, and the atmosphere that makes life possible. Destruction and creation aren't opposite forces. They're two sides of the same cosmic process that has been reshaping our world since the very beginning. Understanding this doesn't make volcanic eruptions less dangerous or tragic for the people affected by them, but it does put them in perspective as part of something much larger and more wonderful than most people ever imagine. We live on a planet that is actively creating itself, moment by moment, through processes so vast and powerful that they operate on scales of both time and space that stretch human comprehension. And this process isn't slowing down or stopping. Right now, new islands are being born in the Pacific Ocean. Right now, new mountains are rising from collision zones where continents crash together. Right now, new soil is being created as volcanic ash weathers into fertile ground. The Earth is younger today than it was yesterday because volcanic processes are constantly renewing and refreshing the planet's surface. You are living through the most creative period in Earth's history. More new land has been created by volcanic activity in the past million years than in any equivalent period in the planet's past. The volcanic system is not winding down, it's speeding up, driven by plate tectonic processes that are more active now than they've been for hundreds of millions of years. This is the great realization. We don't live on Earth, we live in Earth. We're part of a planetary organism that breathes through volcanoes, circulates nutrients through plate tectonics, and maintains its temperature through the balance of creation and destruction that has been operating since the planet formed. Every volcano is a window into this deeper reality. When you see lava flowing from a volcanic vent, you're seeing the creative force of the universe made visible. You're witnessing the same processes that built the continents, created the atmosphere, and made life possible. You're seeing Earth in the act of creating itself. So, there you have it, the incredible story of how volcanoes have shaped and continue to shape our world. We've journeyed from the deepest parts of the Earth's interior, where molten rock currents have been flowing for billions of years, all the way to the surface where volcanic eruptions create new land, new soil, and new opportunities for life. We've seen how volcanoes aren't just destructive forces, but the most creative and essential processes on our planet. They've built the continents we live on, created the atmosphere we breathe, and provided the fertile soils that grow our food. Without volcanic activity, Earth would be a dead, frozen ball of rock floating in space. The volcanic system that drives our planet operates on timescales that dwarf human history, yet it affects everything about our daily lives, from the weather patterns that water our crops to the magnetic field that protects us from cosmic radiation. Volcanic processes touch every aspect of our existence, and this system is still running full speed ahead. Right now, 60 volcanoes are actively reshaping our planet's surface. New islands are being born, new mountains are rising, and new soil is being created that will feed future generations. The earth beneath your feet is younger today than it was when you started watching this video, because volcanic processes never stop creating and renewing our world. Understanding volcanoes changes how we see ourselves and our place in the universe. We're not separate from the geological processes that shape our planet. We're part of them. We're temporary arrangements of atoms that were forged in stellar cores, delivered to Earth by cosmic processes, and organized into living beings by the same creative forces that drive volcanic activity. The next time you see news about a volcanic eruption, remember that you're witnessing one of the most fundamental processes in the universe, the transformation of matter and energy that has been creating worlds and life forms for billions of years. You're seeing the Earth in the act of creating itself, powered by the same nuclear fires that light the stars. This is the science of fire that shapes our world. Not just the fire we can see in volcanic eruptions, but the deeper fires of planetary creation that have been burning since the Earth formed and will continue burning long after humans are gone. We're incredibly fortunate to be here to witness this cosmic process in action and to be part of the most creative and dynamic planet we know of in the universe. If this changed how you see our planet, hit subscribe to explore more incredible stories about the forces that shape our world.